Okay, so let's start, everyone. Um, Nice to meet you. And my name is Wenhai Li. Um, so I'm going to teach this class this semester. The class is my MEC364, Introduction to Fluid Mechanics. I hope you already go through the syllabus I posted on the Blackboard. In the beginning of this class, we will take a couple minutes to, go over the syllabus, so you will understand the schedule of the class and some policies for the class. And of course, you may already know that this class will be an online class, and we will have the class on Monday and Friday between 1 to 2:20 p.m. So we'll meet at Zoom. Unfortunately, we cannot see you face by face, but in this situation, I think it's more safe for everyone. Maybe we are going to have two recitation sessions. They will be held at the same time on Wednesday between 10:30 to 11:25 a.m. Session 1 will be the in-person session, which will be where the classroom will be the free hall 104. And the session 2 will be the online session. The class, we will have a TA for the class, and his name is Ian Bonnell. And he will be, majorly responsible for the recitation session. And the most important thing for the recitation is that this Wednesday, okay, for the first week, okay, this Wednesday, we won't have recitation. Okay, the recitation will start from next Wednesday. Okay, so because that we need a little bit time to to set up some online streaming environments so that both sessions can have the recitation all together. Regarding to the office hour, okay, I will hold my office hour between 1 to 2:30 p.m. From of course by the Zoom, and you can also write me any question by email. If the TA will also have 1 hour 1 hour of for his office hour. And if you have any question for the recitations, you can also ask him. Okay, so let's go to what's this class really will be. Okay, this class is introduction to the fluid mechanics, and so this is a fundamental class for the fluid. In this class, we will basically try to understand the most fundamental concepts, theories, principles for the fluid mechanics, so you can get familiar with those concepts and those theories. Because it's an introductory class, okay, so we are more focusing on the fundamental stuff. We won't, I won't expect you to solve very, realistic, complicated fluid mechanics problem after you finish this class. No, okay, this is just an introductory class. So we go to very fundamental stuff here. And regarding to the textbook, okay, so we are going to using this Willy's textbook, Introduction to Fluid Mechanics. And a couple of the students write me an email to ask me the question regarding the book editions, because that I think currently in the bookstore the edition is 9, and but the latest edition is actually the 10th edition. For the physical copy of the books, actually, I think okay, both 9th edition and 10th edition should be okay, because I try to compare these books. I don't see much difference actually. And the issue is the VD plus, because we need the VD plus to, to do the homeworks, and so that you do need the VD plus registration card. Currently, I'm not sure that the VD plus card you buy from the nice edition, will it also work for the together with the VD plus card you buy for the 10th edition? I'm not sure. I'm contacting both the publisher and the bookstore, the school bookstore, to confirm this. So my suggestion is that because we will also we will not have any homework for the first week. So my suggestion is that right now you should wait for my clarification for this for this book editions. Actually, after I confirm that which edition, especially for the VD plus the access code is working, I will make an announcement on the Blackboard so that you know that which version you should buy. But my guess, okay, I should be both 9th edition and 10th edition should both are okay actually. But just waiting for my confirmation. Since the class is an online class, we will have some special requirements for it. Okay, the class will be delivered by Zoom, and basically I will during my lecture I will share my lecture notes through the Zoom, and we'll discuss those the lecture notes, and I will also make some write some notes at the real time. All the class notes, all the lecture notes, I will post it on the Blackboard after the lecture. The live lecture will also be recorded, okay, and the lecture video will also be uploaded to the Blackboard later on. We will also using the Blackboard a lot, okay. So we will using the Blackboard to make announcement, and also I will assign the homework in VD Plus through the Blackboard, and you will answer the question there. You will finish your homework there, and we will have 2 midterms exam and 1 final exam, and both all the exams will be closed book, and of course because it's online class, you will do it remotely, and some kind of lockdown browser will be used so that when you do the exam, it will be a true closed book environment. So there will be some hardware requirements for it, like you need to have a computer, you need to have a web camera, or you need to have a cell phone so that with the camera. Before those exams, I will make an announcement that the details, how we can do this exams. For the grading, we do take attendance for this class because that we want students to attend the live lectures. I do not want the situation that you just do not attend the class and later on just watch the video on the Blackboard. I do not want that, because I want this class that becomes a little bit interactive between me and you. I may ask you may ask me some questions during the lecture if you have any questions, and also I sometimes, okay, not all the class, I will have some in-class quiz I will post there. So I will using this as a method to record the attendance. For the final grade, the attendance will take 5%, and homework assignments will take 15%. Midterm exams, each of them will take 20%, and the final exam will be 40%. Okay. So there are some general rules we need to attend, we need to be know, because I take the attendance. So you need to, attendance for both lectures and recitations is required. Okay. Also that before each class you need to check your Blackboard, to find the latest announcement for the class, and also some class materials I uploaded here. You can try to kind of get it before the class if there is. And of course, if you have any question, don't hesitate to ask me, both by email or during my office hour. Okay, and on the syllabus, we also have a tentative course schedule here, and we will have basically the class is will be separated to 3 parts. Okay, the first part is we are going to focus on the introduction of the fluid mechanics and also the fluid statics, and this is the contents for the first midterm. From is chapter 1 to 3 on the textbook, and the second part is the fluid kinematics. Okay, and it will be the chapter 4 to 4, 5, and 7. Okay, and the last part will be the fluid dynamics, and it will be the chapter 6, 8, and 9 of the textbook. And we do need to realize that this textbook here, Introduction to Fluid Mechanics, for this class, we only go through the first 9 chapters. Okay. The second part of this book will be used in another class of MEC class. I forgot the number. Is MEC 394 or something? I forgot actually. It's a follow-up class for this one, and so this is the schedule. And the midterm, the final exam will be held on December 17th. Okay, on Thursday, between 2:15 to 5 p.m. Please check your schedule to make sure that there is no confliction of this exam with, with your schedule. And the final exam will cover all the contents of the book. Okay. And so there are some other school policies on the syllabus, so please read it. And so this is what we are. Well, this is what the main what the things on the syllabus. And do you guys have any questions? It's very quiet here on my side, so don't be afraid to talk to me. Okay.
Professor?
Yes.
I just have a quick question. Do we have RO1 and RO2 both on our schedule, or do we just only have one? Because I think I only have RO2 on my schedule.
I think the student each student will be assigned to a single recitation session. Okay.
Okay.
Yeah, if you are assigned to the R01, it will be an in-person session. You need to go to the classroom to attend the recitation. And if you are assigned to R02, you will be a remote session, and you need to attend the class. You need to attend the lecture through the Zoom. Sorry, not Zoom. Actually, we are going to using the Echo 360 actually, and so you need to attend the lecture through the Blackboard. Actually, we will share the link there.
Okay.
Yeah.
Thank you, Professor.
Yeah. One thing I want to let you guys know that for the recitation, we also take the attendance. Okay, at some point. Okay, not all, but just randomly.
Are formula sheets going to be allowed on the exams? Someone asked that.
I didn't decided yet. Okay. It's most likely you are allowed to bring some, some 1 or 2 piece paper, so that you can copy, some equations, some things there. I think it's most likely the way I plan to do. I will confirm this before the exam.
Okay, thank you.
No problem. Any more questions?
Professor, for the online textbook and assignments, is there a specific like code or something for this class section to be enrolled into it, or do we just like, let's say, search it on Google and whatever shows up, we just click into that?
You mean the attendance, or sorry, I didn't got your question. You mean how I check the attendance?
No. For the online textbook, the Wiley Plus, is there a specific code that we're gonna have to use? Because usually, from my past experiences, the professor would give us a code or like a class number, and when you go to these sites, you just put that number, and then it links the class with with our account.
To be honest, okay, I didn't set up the VD Plus yet actually, so I'm also learning how to do that. So that's the reason I suggest you that for the first week, hold on and wait for my confirmation. And I'm contacting the publisher and how to do that actually. I will most likely to set up the VD Plus, this week and later this week, and I will post an announcement on the Blackboard that step by step how you guys can use it actually. So right now, just hold on, okay?
Thank you.
You're welcome. Any other questions, guys? No? Okay, so if there is no question, so we'll start our first lecture. Okay, so I will using this PowerPoint inside a whiteboard environment to deliver the lecture, so that you guys can see the PowerPoint, and in the meanwhile, I can write some comments on the side. Okay. The first chapter is the introduction chapter to introducing like the fundamental stuff for the fluid mechanics. The main topics including that the scopes of fluid mechanics, and basically is that what's the usage, the variable observation, where you can see those kind of phenomena, the fluid mechanics, for fluid mechanics. And we will also define what is really a fluid. Is fluid different with solid? So what is a deep fluid? We will also give you a list of the basic equations we are going to, we need to solve for the fluid mechanics, and different ways to analyze the fluid mechanics problem. And the last thing is we are talking about the dimension and the unit systems. Okay.
Professor, I have a question.
Sure.
Will you be uploading these PowerPoints for class?
Yeah, I will. But most likely I will only able to post the PowerPoint after the lecture.
Oh, but I mean, if you have like a blank copy, so we can maybe annotate it for those people who can, like as you're teaching it.
Okay, I can do that.
Okay, thank you.
No problem. And let me continue. So first question, of course, will be what is fluid mechanics, right? Fluid mechanics is a topic like we study like the fluids. Either the fluids will be at rest or fluids at motion. And also we want to study that how these fluids will interact with other solid surfaces at the boundary of the fluids. Okay, or the interface with other fluids. So as I talked earlier when we talked about the class outline in the syllabus, fluid mechanics basically will including three fields. Fluid statics. So statics means that we study the fluid at rest. There is no motion for the fluid, no velocity. The second part is the fluid kinematics. Basically, we will study the movements of the fluids. And the last part is the fluid dynamics, which will study the effects of various force on the fluid motion and how the fluid is interact with other solid surface, solid body. So there is always a confusion between the fluid dynamics and the fluid mechanics. Okay, so from here you can see that fluid dynamics is only a part of fluid mechanics. Okay, it's just a subfield of the fluid mechanics. So be aware of that. And so why we need to study the fluid mechanics, right? Because that we can see the fluids all around, right? We can observe the fluids, the motion of the fluids everywhere, including the weather and climate. We can see the tornado, we can see the thunderstorm, even the global climate change and the hurricanes. All these are the fluids, either the gas or liquid. And we also need to use the fluid mechanics for the both the aerospace and the automobile industry. Right? We need to study using the fluid mechanics to study both the lift force and drag force for those vehicles. Okay, and the marine, even including the marine ships. So fluid mechanics is also important for the pollution controls, for the environmental study, okay, and such things like to study how the pollutions will be diffused to other to transport to other area, and how the river their hydraulics such as the the erosion of the landmark because the river or to prevent the river flooding. Those kind of things will also involve the fluid mechanics. Fluid mechanics is also using in the medical, like those blood pumps and some like things like ventricular assistant devices. And of course, fluid mechanics you will also see it in some sports and recreation activities, right? So we can study the fluid mechanics to help those athletes to to improve their performance. So all these kind of things will involve fluid mechanics. So that's why it's important to learn. And for fluid mechanics, because we are talking about fluid, right? And we know that there will be 3 phases of matter, right? For the matter, we will have the solid phase, liquid phase, and gas phase. And both liquid and gas phase, we are calling it the fluid. And so we need to understand what's the difference between the fluid and the solid, right? So here will be the definition for the fluid. So a fluid is basically a substance that can deform continuously under the application of shear stress, no matter how small or the shear stress may be. Okay, this definition, please take time, to read this definition. And this definition may be, a little bit, confusing in the beginning, the first time you read it. But the fundamental thing is what it's saying is that different with solid, right? When you have a solid, when you try to put a shear force, okay, either you want to tear it down or you want to just want to deform it, okay. For the solid, you can only to deform the solid to some extent, right? You cannot continuously to deform a solid to arbitrary long, But for fluid, it will be different. Fluid is like it won't have a fixed shape, okay. The shape of the fluid can always changing, okay. And if you apply some force on the fluid, the fluid will be deformed and very easily. Not like the solid. Solid, you have to, have some strong force, to make the solid has the elastic deformation. But for the fluid, it will be different. For the fluid, like no matter, even you put a very small shear force on the fluid, it will start to deform. Okay, their shape will be changed. And so this is how we define the difference between the fluid and solid. And so an example is here. Consider that you have 2 plates, okay, and you have fluid in the middle. And and suddenly, okay, on the top plate, you give it a velocity, okay, and so what will happen to the fluid? And one observation from the experiments we have is that the fluid, there is no relative motion between the fluid and the boundary. What that means? That means is that if you look in this at the bottom, right, this fluid at the bottom, where the fluid is has a boundary with the bottom surface. So at this interface, the velocity of fluid will still keep 0 because that the bottom plate is not moving. Okay, the bottom plate is stationary. So there is no relative velocity between the fluid and the bottom plate at this interface. And again, then if you take a look of the top plate, the top boundary between the fluid and the plate, you will see that the fluid will achieve a same velocity as the top plate velocity u. Okay, the fluid velocity at this boundary at the top will also be this big u here, so that there is also no relative motion between the fluid and the boundary at the top. Okay, and this observation we give a term is called the no slip condition. No slip means that there's no slipping between the fluid and the plate. And why we see this? We will go through this later, but basically you can see, you can view this as it is because that at this interface of the fluid and plate, there will be a friction force. Okay, and this friction force is generated by the fluid viscosity. Okay, we know that all fluid has their own viscosity, right? Like glue has higher viscosity and water has less viscosity. Okay, and this viscosity will generate the friction force between this plate and the fluid, so that they will try to let the fluid at the top gain the velocity of this big U. Okay, and so with this concept, no slip condition concept, so what we will see here is that if we keep let the top plate moving, right, and so the top fluid at the top part will keep gaining velocity, and the fluid at the bottom will still keep stationary, will still keep 0 velocity with the bottom plate. So that what does this mean? This means that the fluid will become to deform, right? The shape of the fluid will be changed. So in the beginning it will be a rectangle, and in the end, and when the time is going, so their shape will be deformed. Okay. And
I have a question.
Sure.
So is theta dot measured in radians per second?
Yeah.
And is it also like for the bullet point where it says undergoes rate of strain theta, is that supposed to be a theta dot?
Yeah, this theta, I didn't go here yet, but I can explain this here. So we can using this angle theta as a measurement for how big the deformation will be, right? And this theta dot, theta dot basically is sorry. So you can looking at this theta dot is just d theta of dt, okay? So this dot means that change between regarding to the time. Okay, so the unit for this one will be the rad per second, right? Or degree per second, or whatever you want to use actually. And we will go through this later, but here is just a peak view that how we calculate the viscous force and the friction force here. So we can know that if it's a Newtonian fluid, this top, the viscous force on the top, will be proportional to this rate of stream. Okay, just to be careful about this term theta dot and theta. Okay, theta. Okay, theta itself is the stream. Okay, it's showing that how the stream will be, and theta dot is the rate of stream. So they are different things. Okay, and based on the Newton's law of the viscosity. Okay, we basically we can define a parameter so that we can calculate tau will be equal to mu times this theta dot, and this mu is called the coefficient of viscosity. Okay, so this is how we define the viscosity. We will talk about this more in the chapter 2. Okay, but it's here it just give you a fundamental idea that how this fluid behavior when you have a strain force, implement on it. Okay, so this is the fluid, but people will think that for the solid, at some extent, right? If it's like a jelly solid or jelly, okay, jelly bean or whatever. If you give some force, put some force on it, it will also be deformed, right? So let's take a look at how the solid, will behave if you put a shear force on it. So you can know the difference between the solid and the fluid. Okay, again, okay, so we have this elastic solid. Okay, and we try to put a shear force on the top and the bottom in the opposite direction so that it becomes shear force. And when it will, this solid can also maybe deform at some extent. Okay, it's not like it can be deformed to very large extent like the fluid. Okay, and this gamma here, as I told you, you can using it as an angle of this change. And this gamma we can talk about is in the solid we can also call it strain. And the force you needed for this shear force top will be proportional to gamma. Okay, and again we can with this law we can have this shear force equal to G gamma, and the G is called the shear modulus. Okay, so compare with the fluid cases we talked before. So what's the difference? The biggest difference you will see that is that in the fluid, okay, your tau, your shear force will be proportional to the rate of strain, theta dot, not the strain itself. But for the solid, your tau will be proportional to the strain itself. Okay, so this is the biggest difference here. And fluid is for rate of strain. Okay, the tau will be proportional to the rate of strain, and for the solid, this tau will be proportional to strain itself. Okay, so for strain itself is so for strain itself for this one, okay, the angle maybe just the degree, okay, but for this one, so rate of the strain, the unit will be rad per second. Okay, so this is the difference between the solid and fluid. So which means that in the fluid, this deformation is determined by the rate of the strain. And another thing that you can view the difference between the solid and fluid is that for the solid, okay, their deformation has a limit. Okay, we call that elastic limit. Okay, so if it's larger than the limit, your solid will not able to deform anymore, and sometimes it even can break. Okay, and so if you're looking at this picture here, if as a steel, okay, it can be either solid or fluid, and if you try to give a force on the top, both solid and fluid can deform to some extent. But if you keep increasing, keep applying this same amount of force on the top, the solid will only able to deform to some extent and then stay there. They will not able to have the deformation anymore. But the fluid will be different. The fluid will be still continue to change the shape, have some continuously. And when the time is going on, the fluid, this shape of the fluid will keep changing. Okay, and this is how the difference of the how the difference of in behavior if both a solid and fluid, we put a shear force on it. And so now let's go back to the definition of fluid. So with all the discussion we have so far, so let's review this definition again, so you will have more understanding that what is a fluid, right? A fluid is basically fundamentally a substance that will can deform continuously, okay? So the crucial term is this continuously. And when you have a shear force, and no matter how small this shear force will be, okay? So by using this standard, we can define that we can make the difference between the fluid and solid. And as we talked before, right? Between in the three phases of the matter, both the liquid phase and the gas phase we usually consider they are fluids. Okay, but they are, although they are both fluids, but they are really, and there are some difference between them, right? For the liquid, we know that liquid in the liquid phase, the material molecules, they are spaced more closely, right? The intermolecular force between in the liquid is strong, okay, is very strong, but not as strong as those in the solid, okay. And the liquid can flow, okay, and if you put the liquid in a container, okay, and due to the gravity, okay, it will keep their shape, okay. So if you have this container here, the liquid will stay at the bottom due to the gravity. And even without the gravity, okay, and the liquid, they will also try to stay together because this intermolecular force, okay. And for the gas, it will be different, okay. For the gas, because the gas molecules, they are spaced very widely. The distance between molecule to molecule is much larger than those in the liquid, so that the both the attraction and the impulsion force between the molecules is not as strong as those in the liquid, okay. And if you put a gas into a container, okay, and gradually, okay, this gas will go to everywhere inside this container. And this is the major difference between the liquid and the solid. Sorry, between the liquid and the gas. Okay, so we spend a couple of minutes to explain what's the difference between the fluid and the solid, so that we can define what is really a fluid. Do you guys have any question here? So before I go to the next topic.
Yes, Professor?
Yes, please.
So because we're considering fluid as an element that undergoes deformation, should we consider it as a mass that changes or a volume?
It's volume, change of the volume. The mass
Okay.
will not be changed.
Oh, right.
It will be conserved.
Yeah, because I understand that it's not just one particle we're looking at, but
No,
whole
yeah,
element.
okay. The total mass will be conserved.
Okay.
Any other question? Okay, so if no question, let me go to the next topic. So this some the overview of the analysis method we use to study the fluid mechanics, right? And so basically, we can separate the method into three groups. The first one is analytical analysis, and which is the major content of this course. In the analytic, we're using using this analytical method, the math, okay, and the fundamental basics to study the theory behind the fluid mechanics, okay. And will apply the control volume or differential analysis to try to derive the, the governing equations, which can be used to solve the fluid motions. And for some simple geometry, okay, for some simple cases, we can even using this analytical method, just using the math, okay, we can derive the exact solutions. So all this belongs to the analytical analysis, okay. So it's analytical analysis is the most important part, okay, because it provides the fundamental theory for the other two methods. The other two methods, one is the experimental analysis method, and one is the computational analysis method. The experimental analysis method is by the name, okay. It's like we do experiments, okay. We're using different measure tools, to equipments, try to, measure the flow, behavior for different kind of problems, fluid mechanics problems. And after we got the experimental data, and we can use this data try to do further analytical analysis on this experimental data so that we can have new theory developed. Or we can also, using this experimental data, try to derive some empirical formulations or table, which we can, use in industry, okay, in the engineering, real engineering problems, okay. So experimental data analysis is also very important because that it provides the way that you can validate your theory, okay. And also it provides a way that if your theory cannot solve the problem, at least we have some way that we can do experiment to try to get the result, so that next time when we have a similar problem, we can just use this experimental data directly, okay. And the last way is the computational analysis, okay. And this is the way is only available after the development of these computers, okay, computational devices. And basically it will, we basically in this method we will write computers codes or softwares, using the computer, try to solve the governing equations which we developed from the analytical analysis, and apply this try to solve this equation by computer for some realistic problems, and using the computer to solve to get the result. And it's very powerful, okay, because that after your program, okay, your software, your computational code is finished, it's complete, you can reuse the code to do arbitrary problems as long as you have enough computational resource, okay. And for some problems, you may find that it will be very expensive, or maybe you are unable to do it by experiments, okay. You like if you want to, for example, if you want to send a rocket, okay, send a satellite to the outer space, right? You won't be able really to do experiment for that, because that it will, you cannot just spend like billions of dollars to just send a rocket, send a satellite to outer space, just try to get the experimental results for it, and without knowing that it will succeed or not, right? It's too expensive. But you can do that kind of thing by computer, like you can simulate, this kind of behavior, by computer before you do the real, the real launch of this satellite thing, okay. And before you do that, you can use a computer to design, to estimate all the conditions to see that if this can succeed or not, if the, the design is correct, design is accurate for both rocket and satellite. You can do that. Okay, so this is how this showing that the computational analysis is also a very powerful method you can use actually. And again, okay, we have this 3 methods, and because this class is the introduction class, and we'll most focus on the first analysis method. We'll mostly focusing on the analytical analysis method. So in this basically means that we are mostly focusing on the basic theories, governing equations, how to derive those governing equations, fundamental concepts, and those kind of things. Okay, and for the other 2, you will be able to learn it in other classes. And when we're talking about the fluid, right? And the fluid will have their properties, right? We need to using properties to define the state of the fluid. And we can categorize those properties into different groups. Okay. And the first group is the kinematic properties, such as the linear and angular velocity, and the rate of spin, vorticity, acceleration, and each other. Okay, so this is called the kinematic properties. And we will also have the transport properties. Transport properties such as the viscosity, thermal conductivity, and the mass diffusivity. Okay. The reason we call this transport properties is because that these properties is involved in the transport phenomena. For example, okay, viscosity is involved to the, when we know that viscosity, you can use viscosity to calculate the friction force, right? And we know that the force will change the momentum, okay, of the fluid. So you can thinking that viscosity is a properties involved when you transport momentum, okay? And if you took the heat transfer class, you will know that thermal conductivity, you can use it with the Fourier's law to calculate the heat flux in the heat conduction, right? And so this is heat conduction is also a process where you transport the thermal energy, okay? And the mass diffusivity is another is another property involved in the transport of the mass, okay? The mass with some high concentration, will be diffused to the low concentration area, okay? So that's why we call this transport properties. And the next group is called thermodynamic properties, okay? Because that these properties is used to define the thermodynamic state. I think most of you already took the thermodynamic class already, okay? Because it's a request for you to take the thermodynamics before the fluid mechanics class. Okay? And we know that in thermodynamics we can using these properties, right? Pressure, density, temperature, internal energy, enthalpy, specific heat, and etc. Okay, to define a state, right? So when we have when we have pressure, density, temperature, for example, for the ideal gas, we can see that we can define this state for thermodynamic state for this ideal gas. Right?
Excuse me, Professor.
Yes.
We didn't take thermodynamics yet. We're taking it like this semester also.
Oh, really? Okay.
Yeah. So we might need some extra help when you explain the thermodynamic concepts.
Oh, okay, no problem. So in the cases that the thermodynamic concepts is involved, I will try to explain it a little bit more. Okay. Thank you. Thank you for letting me know. Okay, for letting me know.
You're welcome.
Okay. Okay, and the last group is some other properties like the surface tension, vapor pressure, which will be used for the phase changes between liquid and gas, those kind of things. Okay, so this is most seen properties for the fluids, and some of them, okay, we will go into details in the next chapter, and so on. Okay, so this is just a fundamental introduction of them. And we have the properties, right? And then we will also have the equations. You know, equations means that you know, using the physical law, you know, to group those properties into some equation, right? Some formula, and so that you know, it can you can follow some very fundamental, you know, physics laws. Okay, the laws in the physics, we can separate them into two groups. Okay, one group is called the basic laws. The basic laws means that it's really the fundamental laws that no matter what kind of material it will be, you know, in all the situation, this law need to be, you know, will need to be satisfied. Okay, this law will govern all the problems. And the second group of the laws we call the particular laws. And for the particular laws, those kind of laws is not working for all the materials. Okay, maybe those laws only working for a small group of materials, small group of medium, or only valid for some specific conditions. And that kind of law we call it the particular law. Okay, so let's first talking about the basic laws will involved in the fluid mechanics. There will be 5 laws involved. And the first law is conservation of the mass. Okay, conservation of mass basically means that you know, the overall system, in the overall system, right, there's no mass creation or destroy. Okay, the total amount of the mass will be a constant. Okay, because we didn't consider the nuclear reaction. Okay, so there is no, you know, transition between mass and energy in fluid mechanics. Okay, so that's why we see that in fluid mechanics, the mass will be always conserved. Okay, this is the first basic law. And the second basic law is Newton's second law of motion. And we know that the second law, Newton's second law, is between the force and the mass acceleration, right? Yeah, another way to view this law is that Newton's second law basically tells us that how the momentum will be changed if you have a force, right? And so if you're also looking at the force, if you also, you know, look force as some momentum, and sometimes we also call this law the conservation of momentum. Okay. So when we're talking about conservation of momentum, they are the same thing with the Newton's second law for the fluid. Okay. So basically, it will involve the force and the momentum. Okay. And the third one is also between the force and momentum, but we are looking in the rotational way. Okay, rotation. So this is also, you can also call that this principle of angular momentum. You can also see that this can be something like a conservation of angular momentum. Okay. So the torque you put on this on the system will be, you know, conserved with the change of the angular momentum. So, and both these two, okay, actually they are the same one. Basically, you can all call this, both these two is regarding for the momentum of the system. And the last of two is regarding to the thermal energy, or regarding to the temperature, or other kind of energy like the kinetic energy and the momentum energy. Sorry, kinetic energy or potential energy. Okay. So you can think like the first equation is for the mass, and the second and the third is for the momentum, and the last two is for the energy. Okay. What is the first law of thermodynamics? Basically, the first law of the thermodynamics just means that the conservation of energy. Okay, so this is identical to the conservation of energy. And what the energy is defined, E here, is defined by 3 parts. Okay, it's defined by the kinetic energy. It's defined by the potential energy, your energy due to the gravitation, and also you are defined. You are also including the thermal energy. So this is called the internal energy. If you take the thermodynamics, you will know this. Okay. The internal energy is also can be called the thermal energy. Okay? Okay, so basically the first law means that this E here for the whole system will be conserved. Okay, maybe you have the transition between the kinetic energy to potential energy, or this mechanical and all this kind of thing is also can be called the so maybe let me leave it alone. Okay. Also you can convert this kinetic energy, potential energy to the thermal energy. Convert from the kinetic energy to increase the temperature of the system. It's possible. Okay. But the overall amount of this E, which we call the total energy, will be conserved from the whole system. So that's the reason why we call this first law of thermodynamics also identical to the conservation of energy. And the last one is the second law of the thermodynamics. And the second law of the thermodynamics is basically telling us that there will be a direction for the heat transfer. Okay, so we know that the heat is always transferred from the high temperature to the low temperature, right? So you cannot let the heat transfer from the low temperature to high temperature without using any other external means. There's no way to do that. Spontaneously, okay, the heat is only transferred from the high temperature to low temperature. So there will be we call the unidirection, okay, for the heat transfer. And this is what the second law of the thermodynamics is talking about. Okay, it's basically showing that for the heat transfer, there is a unidirection behavior, and thermal energy is only transferred from high temperature part to the low temperature part. And this is what the second law of the thermodynamics. Okay. And so in this class, okay, we are mostly likely to using the first 4 equations, and the last equations we do not need to. The first 4 equations will give you the governing equations for the fluid mechanics. Okay, the governing equations basically will include in the conservation of mass, conservation of momentum, and conservation of energy. Okay, we will develop the governing equation for these 3 things. And the last one, since it's just telling there will be a fundamental direction there, so it's not a formula. Okay, okay, and they will be implicitly involved into the energy equation. Okay, so this is the basic laws, right? And as I told you that instead of basic laws, we also have some particular laws, right? Not those particular laws is only work for a certain medium or certain conditions. And one example is the ideal gas of equation of states. Okay, and we know that this P equal to rho RT is only work for the ideal gas, right? And but we also realize that in the realistic case, okay, we if the gas we have around in the atmosphere or in other experimental conditions, they are close to the ideal gas, but they are not ideal gas, because the ideal gas basically means that from the physics view, okay, basically means that there is no intermolecular potential field, which means that the attraction force and repulsion force between molecules can be neglectable. But this is not really the cases. Okay, that's why that this ideal gas is only valid when you have a very low pressure, low density case. Okay, and if your pressure and density is high, very high, usually you cannot just use the ideal gas of equation state. Okay, by looking like this way, okay, you will know that we have this equation, but this is not a basic law. But it's not a basic law doesn't mean that it's not important. Okay, we still need these laws, okay, because that the governing equation itself sometimes is not enough to solve the problem. Why? I can give this example later on of the when we're talking about lecture 3, when we're talking about the governing equation. The basic reason is that when we have the equations, right? We want to use this equation to solve unknowns, right? The ideal cases is that if you have like 3 unknowns, we need to have 3 equations to solve, right? But the problem is that if you taking a look over this basic laws, okay, we have the conservation of mass, equation 1. We have the conservation of momentum. If we consider 3D cases, we will have 3 equations. So consider momentum on the x, y, z direction. Okay, so we have 3 equations for the momentum. And when we consider the conservation of energy, the first law, we will have 1 more equation. So altogether, we will have 1 plus 3 plus 1. We have 5 equations, right? So let me give you an example. We have like we have 1 mass flow mass equation. We have 3 momentum equation, and we will have 1 energy equation for 3D cases. So altogether, we will have 5 equations, right? But how many unknowns we will have? So we will have 5 equations. How many unknowns we will have? We do not know the rho, right? We want to solve the fluid density. We do not know the P. We do not know the T, temperature. So this is 3 fundamental thermodynamic states properties. We do not know the U, velocity on the 3 direction. Okay, and so take a look of this. So we will have 6 unknowns. So this means that the number of unknowns we have is more than the available equations we have. So we are not able to solve this governing equation, these 5 equations directly to get all these 6 unknowns. And in these cases, which means that we have to bring the additional particular laws, additional relations to the governing equation so we can solve it. For example, one example is that if we bring this ideal gas equations to this governing equation, ideal gas equation to this equation. So now we can have 6 equations, and then we can able to solve these 6 unknowns. Okay. So this explains that why in some situation, okay, we will need additional equations, additional relations, and we call these relations particular laws. And other particular laws will involve that Newton's laws of viscosity, which I showed you before, like tau will be equal to viscosity times the change of the strain rate, right? In these cases, in the fluid will be change of velocity on the space distance, so we will du dy. And if you're looking like consider the mass transport, you will also have this fixed diffusion law as another example as the particular laws you may need. And Fourier's heat conduction law, where you calculate heat flux based on the temperature gradient with this thermal conductivity here. So all this kind of laws is the example that the additional laws may involve. Okay, and these two we will need in the fluid mechanics class, in this fluid mechanics class. Okay, All right. So before I go to next topic, do you guys have any question regarding to the this properties and these equations we are going to use? Any question here? Okay. Yeah. So this is just a your introduction for these equations, right? So in the upcoming lectures, we will go through very details for each governing equation, how to derive them, and how to solve them. There will be an example problem for the for this how to do this energy balance and energy conservation, and I will leave this to the recitation session. Okay, and the next two concept is the system and control volume. Why we need this concept? This concept is used to derive the governing equation. Okay, we have those conservation of mass, right? We have those conservation momentum, and we have this conservation energy. But when we try to derive these conservation equations, we need to study. We need to have some objectives to study, right? We want to know that the conservation mass is regarding to what kind of region, right? What kind of fluid, what part of fluid, what part of space, what kind of container, those kind of things, right? So this is what the systems and control volumes mean. And basically the systems is just like it's closed, okay? We call it a closed environment, which means that for example, in this picture here, we have this piston piston geometry, piston cylinder geometry here, and inside this piston we have this part of the gas. Okay, we have gas inside, and by changing the weight of this piston, right, we can try to compress this gas into different volumes, so that so if I put more weights on the top, and the volume of this gas will be decreased, and the pressure of the gas will be increased, right? And in this system, we can define this container for this gas as a closed system. The reason we call it closed is that across the boundary of this gas, this system, right, there are no mass flow in and flow out. Okay, there are no flow can flow into this environment and flow out of this environment. And that's why we call it a closed system. Closed means that no mass flow into or flow out. Okay. And the second way term is called the control volume. Okay. Control volume, it will be different with this system because it will become open. What open means that across the boundary, the flow the mass may be flow in or flow out. Here is an example that how we define a control volume through in a pipe junction. Okay, so we can define this control volume using these blue lines here. Okay, and this will be the boundary of the control volume, this blue line, and we can see that at this boundary here, the flow can flow in, and at the boundary at the bottom and the boundary at the right, the flow can flow out. Okay, so this is what we mean open system, because the mass flow can cross the boundary. Okay, and this control volume, the second term, the volume means that this region is defined by the space coordinates. Okay, we only define this control volume as a specific region, space region. Okay, and let's talking about a little bit more what the system and control volume means. Okay, so basically a system is defined as a fixed, identified quantity of mass. with the. So that means that the total mass inside of the system will be not changed. Okay. And but this system can move. Okay, it's not necessary that this system has to be stationary. You know, let's go back to the example of this piston cylinder configuration. As I told you that if you try to increase the weight or decrease the weight of this piston here, you know, these guys, you know, the volume of this gas can be changed, right? Can be increased or decreased. And so when this, you know, so when this cylinder volume is changing, and you can read your system, their boundary will also be changing, right? If it becomes smaller, this system will become smaller, and if it becomes larger, the volume increase, this system will also be increased. So that means that that's what it means, that the boundary of the system may also be movable. Okay, but the most important thing is that in the system, that means that there's no mass across the system boundary. No, there's no mass flowing into the system or flow out the system. And the control volume basically is not defined by the mass. Okay, so system basically you can see that you know identified by mass. Okay, so that means that you know identifiable quantity of mass. And in the control volume, it's not identified by, it's identified by space coordinate. Okay, so we identify this. When we define a control volume, we just give the XYZ location, okay, of this control volume. That's it. We do not care that you know which fluid particle is inside this control volume, whether or not this particle will flow in or flow out. No. Okay, we're just using this physical location XYZ to define this control volume, and the flow can you know, this fluid can flow in, flow out. It doesn't matter. But in the system, you know, we need to know that you know what the mass inside. And for example, if this gas, we will know that these particles, if it's gas, this gas molecules will be inside this system, and they will always be inside this system. Okay, and these particles determine that what's the boundary of this system. Okay, and so for the control surface, so the boundary for the control volume is also called the control surface. You know, in the abbreviation, sometimes we write it as CS, and the control volume sometimes we write it as CV. Yeah, and this surface, control surface, which means the boundary of the control volume, can be real or imaginary. Okay, so in these cases, it will be real. This boundary is real around the pipe, along this pipe solid. But this boundary here, this inlet boundary, this outlet boundary, they are imaginary. Okay, this is not a physical boundary, but we just you know define it, define this part as the control surface for the control volume. Okay, so this is the two concepts: control or closed system, open system, control volume. And regarding to the fluid, regarding to the thermodynamics, okay, in the thermodynamics is using this concept system a lot. Okay, if you took your thermodynamics class, okay, you will using this system definition a lot. And in the fluid mechanics, we usually using concept of control volume. Why? It's very simple, right? Because that in the fluid mechanics, it's very hard, you know, try to track all the fluid particles, right? It's very hard to do that, you know. And we have a lot of fluid particles, and they are keep moving, but especially for the gas. You don't know, you don't know that where it will go, you know, in a very long time, right? It's very difficult to, you know, try to identify all the particles, fluid particles in the fluid. so that's why in the fluid mechanics, we're using this as control volume theory, control volume concept a lot. And with this control volume concept, and then we can apply this basic laws: conservation of the mass, conservation of momentum, and conservation of energy, right? So, for example, for this control volume, right? And if we could apply the conservation of mass for this control volume, what will it look like? We will know that the mass flow in plus mass flow out. No, not plus, sorry. This one. Minus mass flow out will be change of increasing of the mass overall mass flow, mass inside the control volume, right? So by doing this way, we can apply a mass of conservation to the control volume. And in this way, in the system, if we want to apply the conservation of mass, that will be very simple. M equal to constant, that's it. Because that there's no flow in, no flow out. But in the open system, like the control volume, so this is the form will be what the conservation of mass will be. So mass you flow in minus the mass you flow out will be the increase of the mass inside the system. Okay, so this is the difference between the these two concepts, the system and the control volume. Okay, we have 2 minutes left for this lecture, so I would like to stop here. And do you guys have any question regarding to, this system and the control volume?
Yeah, Professor, I have a question. For the controlled volume system on the bottom,
yeah.
the blue dashed outline and the black pipe are both controlled volume, but one of them is real and one of them is imaginary. The blue is the imaginary, I'm assuming.
Yeah, because that at this part from here to here, you can think that this blue boundary, control volume boundary, is a physical boundary because that they are coincide with this pipe, solid pipe surface, right? And from this part to this part also, you can see that this boundary of this control volume is a real boundary. But for this part here, and this part here, and this part here, it is not a real boundary. So it's become an imaginary boundary. Okay, so in this case, this will be imaginary boundary. And it's not necessary necessary you define the control volume in this way. Okay, not necessary, because as we already mentioned, that the control volume can be arbitrary volume. Okay, you can define the control volume in any way. In this case, I can even define control volume just here. Okay, I can just define that this part as a control volume. It doesn't matter to me. Okay, and so in this case, all these 4 boundary will become imaginary. This will not be the physical control volume. And I can also apply the mass conservation, momentum conservation on this control volume here. But the disadvantage is that the problem I resolve is only for the fluid in this part. It's not like for this one, I can resolve all the fluid in all the part here, because that it's important that we want to solve the fluid around these surfaces so that we can know what the friction will be, what the friction will be, so we can know that what the pressure drop will be when the flow through this pipe junction. Okay. So just be realized that this control volume it's just designed by the space coordinate. It can be arbitrary. You can even define a control volume, outside of this pipe. It doesn't matter. But the problem is that if you design this way, you will also need to solve what the physics is here, physics here, physics here. It's not necessary in this case in this problem. Okay. Do I answer your question?
Yes, thank you.
No problem. Okay. Any more questions, guys? Okay, so if there is no question, we will just stop here, and we will continue on Friday. And I will post this lecture notes on the Blackboard today, and also post the this lecture videos because I recorded. And just remember that we do not, I want to say it again, okay? We do not have recitation this Wednesday, okay? But we will have, the recitation will starting from the next week, okay? And okay, that's it, okay? I will see you guys on Friday.
Wait, Professor?
Yeah, yes?
So are you gonna upload both the document that you write on and the document before you write on it, so before class students can also like review the notes as well?
Which way you prefer? Because that my handwriting on this screen is not very good. I know that because it's not easy to write on screen.
Yeah. I mean, if you're able to post both, like both before and after, like last year we had our solids professor, you would upload the notes and then you would upload the annotated notes after as well.
Okay, okay, I will post both.
Okay, thank you so much.
No problem.
Have a good day.
Have a good one. No, if there is no question, I will just stop here. So if you have any question, regarding this course, write me an email. And on Wednesday, I will have my office hour. You can also, talk to me at that time. Thank you, everyone. See you on Friday.
Thank you.
Thank you. Bye.